Hello and welcome to the third and final day of the Argus 144 conference. Today is a mix of both science presentations and discussions on the type of support that will be needed to really bring this instrument to be a world-class facility and easily usable by astronomers around the world. So our first presentation today is by Professor Erik Rosolowsky from the University of Alberta, and he will also be leading the final wrap-up discussion we have at the end. As a reminder, we will also be having a poster discussion in the last hour of this, so feel free to go to the website and browse through those posters at your leisure. So I will turn it away right now to Erik Rosolowsky.
Thank you very much, Will. Thank you to everyone for dialing in this morning. Today, I'd like to talk about the data and software requirements for the Argus Plus instrument. By the end of this talk, I hope to show you that there is a small data challenge associated with the Argus Plus instrument, but that we have the tools and capacity to meet that with experience that we've already gained through previous instrumentation and surveys we've carried out on the GBT. So I think of the Argus Plus software development requirements in kind of four different domains. We have the data and observing management, which is the software that's required to actually get the telescope to execute the observations. The calibration of the data that will come out of the instrument. Mapping that is going to be required to take the spectroscopic data and turn that into calibrated maps. And finally, the analysis software that we're going to require to get data turned in the maps, turn that into basically the science papers that we need. So if I think about the data flow for the Argus Plus instrument, largely in the form of a block diagram here, where everything we've talked about so far today is in the first stage of this block diagram, really the telescope to the front end to the back end, shown here as the spectrometer. But today I want to talk a bit about how we're going to go from that spectrometer into the calibrated data cubes that we're going to be using for science. The fundamental product that's going to come out of that spectrometer is basically going to be counts versus channel. Spectrometer counts as a function of spectrometer channel. And that's going to get dumped into a file system that will then act as kind of the archive. And from there, it's all these computing and software pieces that we're going to take the calibration information to turn that into astronomically relevant intensity and frequency spectra versus time, and then turn that again into intensity versus frequency as a function of sky position, which is the product that we really want to focus on to do our science. The pieces that we'll talk about briefly today are going to be the calibration step, which is how we're forming signal reference pairs in the data set and how we turn that into antenna temperature. Then we're going to talk about briefly the tuning metadata and get that onto the sky frequency. We'll talk about methods that we've been using for flagging bad scans, which is an important part of producing good quality data products, baseline subtraction, averaging and downsampling to manage a bit of the data challenge, and gridding data into the position, frequency, or velocity cubes. Now, what's kind of interesting that I found out with the Argus instrument is that there's a fairly substantial data rate coming off of the instrument if you're operating at full out. So I just, my back of the envelope number here is to take the 144 feeds of the receiver, multiply it by the nominal 131,000 channels, and a 7 millisecond dump time that we were talking about to get the fast mapping rates, and using 1 byte for your bit depth here, you're putting 8.8 terabytes an hour into your processing file system. And if you're like me and you get the emails about the Luster file system at Green Bank being pretty full, this is really only going to add to the concern about the data stored on site. Fortunately, the downstream side of the data challenge isn't as daunting. If we take one of those full degree maps that we're talking about, have it be fully sampled, even at this maximum spectral resolution, and looking at this as a float representation, we're going to end up with a half terabyte cube. This sounds challenging right now, but thanks to efforts largely driven by the Square Kilometer Array data challenges, we're actually able to have the tools we need to navigate and analyze these very large data cubes. Now, these are extreme numbers. I've kind of put up our worst case scenario for the data challenge here. And there's a lot of ways that we can address this naively. The simplest one is that if we're operating Argus in this nominal configuration full out, much of our bandpass isn't really going to be filled with interesting data. I'm a big fan of keeping noise because it tells you a lot about what the instrument is doing. But even so, you can probably throw away about 90% of your bandpass for a lot of the science cases that we're talking about and still have enough to do good calibration and understanding of your spectroscopy. Similarly, this is very high spectral resolution that we are sort of mapping out that 600 megahertz of bandwidth. And so we could actually downsample here by smoothing and resampling down to a lower spectral resolution, because you only need a few channels across the line width of your line to have all the information in there. And typically we have, a small data loss of about 5% from data flagging. To meet these challenges, I want to talk a bit about some progenitor surveys that have helped us get to where we are. And this started with the Green Bank Ammonia survey. And Rachel Friesen talked about that yesterday. And Rachel, working with Jaime Pineda, led us through this mapping exercise with the K-band focal plane array. And that really laid the groundwork for some of the software that we needed for large-scale mapping surveys. Using the Keystone survey, we extended that challenge by taking this KFPA mapping and really pushing the Vegas correlator all out. We used the ramp spectroscopic survey, setup with a very fast dump time and really the shortest possible frequency switching time to get to the results that we need for this Keystone project. And that really challenged us on how to operate large spectroscopic data volumes coming in. And finally, Amanda Kepley spoke yesterday about the Degas survey, which she is leading. And what's happening here is we're using the actual Argus instrument to carry out an extragalactic survey of very faint spectroscopic lines, here mapping 36 nearby galaxies in these dense gas tracers. And the key point here is that this is using Argus, so it's going to be a very similar technology to what the Argus Plus instrument would have. Plus, we're really having to focus on good performance and very stable spectroscopic data products to see these lines in these faint lines and really drilling down in terms of sensitivity. So we want to make sure we're averaging down correctly to get to the thermal noise level. So just stepping through a few of the steps that these progenitor surveys have given us in terms of guidance, one thing that we faced a sort of development on with regards to Argus 144 would be how we're actually doing our calibration and switching. We talked a lot about the frequency switching methods so far. That works especially well for narrow spectral lines like what we would see in these galactic science cases. But this frequency switching does actually have some Doppler tracking concerns. So we'd have to think about how to Doppler track effectively as we're mapping at these high dump rates across the sky, or we could adopt the strategy that we use in Keystone, where we only take a finite number of Doppler tracking scans, in Keystone's case, at the row ends, and then we turned off our Doppler tracking and just interpolated across the samples. So here, these little schematics that I'm showing you here, the blue points are representing the dumps from the spectrometer as they would appear as we trace across the sky. And we would only actually do Doppler tracking at one end or the other of the rows. And that'll give us a sense of and then we just interpolate across that to register the data to the sky frequency frame. And then we do all the shifting of our data ourselves, just using transforms in our data pipeline. The next obvious thing is to do a position switch with a fixed off. This is a fairly low efficiency observing method because you have to steer off to some part of the sky. And you also have to know that that part of the sky is blank. So it can be an effective sky reference. But nonetheless, this gives us kind of the best sort of stable off positions if we know that it's emission free and we're observing at similar air mass. Finally, one thing that we adopted in the Degas survey was to actually use off regions defined within our map. So we never steered off to a different place in the sky. We just knew what part of the sky was going to be blank. And here we know that because we've already observed a lot of these targets, these nearby galaxies, in carbon monoxide emission, which is really bright compared to the lines that we want to see. So what we've done is when we have the maps track across the galaxy, we keep track of where we expect to see the CO emission. And those points here are the dumps that I indicate here in orange. And everything that's not part of those dumps counts as an off position. So we just pick our offs out of the map. And when we look at that in the raw data domain, this is the dumps coming out of the spectrometer, we have the channel in the horizontal axis of the figures that you see here. So each row in these figures is a spectrum. And then as we move through time, we get each row added to this 2D image. And we identify those regions in this 2D image where we're going to have emission in the maps, and we ignore those, and then we fit the off position, a smoothly varying model for the off, to the remaining data. And this gives us a smooth model for the reference that we then use in our data calibration. So the next thing that we've had to learn about in the pipeline development was the idea of automatic scan flagging. This has been really important for the Degas survey and using the Argus instrument because we get occasional things happening that we need to just clean out of our data. Really, you can see those features here in the image. Again, this is a plot where each row is a spectrum and it's shown over time, and the color indicates the brightness of the emission. So you can see individual spectrometer spikes showing up here. Those are those long vertical lines here. Those are cases where the spectrometer is just giving us a bad channel. You can see a low order baseline ripple when these large areas of red or blue in the plots. And then occasionally our calibration method or Vegas, something goes wrong for a row in our map, and we need to be able to identify where that happens and blank that out. The key tool that we use is the radiometer formula. So we use the thermal noise that's expected from the system temperature, integration time, and channel width, calculate the thermal noise, look at the noise in the spectrum, and if it's significantly larger than what's expected from the radiometer formula, we go ahead, reject that scan. Similarly, we use spike flagging to find channels where they are substantially different from their neighbors, blank out those, and then we attempt to fit baselines. And if we still have residual baselines or ripples, we also reject those scans. Given that, we can actually take this map and clean it up by getting rid of all of those bad data here, and we end up with something that looks a lot like blank noise, but buried within here is our faint extragalactic signal.
2-minute warning, Erik.
The final part of our mapping software is built into the mapping and the gridding. So what we do is we take those spectroscopic dumps shown here in blue, and we turn them into a cube map on the sky. And so we take each pixel here, shown here in yellow, and we calculate a weighted average of all the spectra around it, where the weight in that weighted average is defined by the mapping kernel. For example, see the Mangum and Wooten on-the-fly mapping article for examples of different kernels you could use, and we calculate the average spectrum to figure out what represents that point in the PPV or PPF data cube. What was novel about our approach is we actually accumulate the top and the bottom of this sum separately. And this allows us to do the mapping or the gridding step in parallel. We could split it over multiple processors and then just sum the copies of the numerator and the denominator in this average to produce the final data set. You can also incrementally add data to your map by tracking these two parts separately. The final part that I'm not going to discuss a lot is analysis, but I'm going to highlight this as something that we should discuss further at the end of the day here, which is what are the tools that we'll really need to meet the Argus data challenge. And that obvious one is signal identification and masking here. But yesterday, Brian Svoboda brought up the challenge of fitting multiple velocity components, specifically of lines with multiple hyperfine components, as a pressing data challenge. And there's been many, many different methods that have just come out in the past few years, including Brian's method that I highlight here in the figure. But this is going to be instrumental for addressing a lot of our science cases. Here, performance is the main area where we're going to need to look to improvement. We want to understand these fitting methods in great detail and figure out how to really enhance their performance so they can operate on these half-terabyte data cubes effectively. Of course, not all of that will be filled sky, but we will get to improvement. We will get to improvement in performance to yield these science goals. So I hope to discuss that a little bit later in the discussion section, along with the questions of data and observing management. Some things that came up a little earlier in the conference was the idea of how we manage our queue scheduling for these observation blocks in large surveys, and how we use the data to actually use the metadata for the survey to process the pipeline. We've talked a bit about calibration and mapping so far, and then I hope we also discuss analysis here. So I hope you're left with an idea that we do have a bit of a data challenge with Argus Plus, but we actually have a lot of the tools that we need to solve it. And especially, I want to highlight that calibration, mapping, and a lot of parts of analysis can be done in parallel processing, which allows us to leverage computing. And often this is embarrassingly parallel. So simple people like me can actually figure out how to use multiple nodes to attack a lot of these problems. I'd be happy to take any questions at this point.
Thank you, Erik. Our first question is, how did you keep track of progress of observing programs? For example, given bad weather and technical problems only becoming obvious during the actual observations?
That's a great question. I won't pull up, but we actually did the dumbest possible thing, which is we have a Google spreadsheet, and we would track all of the features of an individual scan per Google spreadsheet, which we then would pull from the web into a CSV file. And the pipeline framework that we have parses that CSV file and is able to identify, use that to actually track how we're gridding, associating scans with objects, but it's also a place where observers can enter in notes like, this is bad weather, we shouldn't include this. And we can also update whether a certain scan block should be included in our survey or not. So we have one master Google sheet, which was pretty easy, I hope, for the observers to use and keep track of the survey status there. And that also was the file that drove our pipeline data processing.
And we have one question. I will enable them to speak. Go ahead.
Sorry, no, it was a question so that I could be added to the panelist list for the next talk.
All right, well, we will mute you again. Thank you. So there's another follow-up to that previous question. So you need to be able to process that data live.
Yeah, so to be clear, when we were doing our previous surveys, we would have the existing logs updated. We would pull the logs down and then post-process all of our data into the final data products. I would say for Argus 144, a challenge that we should sort of discuss in the afternoon session is how to push towards being able to essentially get cubes as close to instantaneously as possible, so we can understand how we are actually, how the observing is progressing and being able to modify on the fly. A lot of the I guess, advantage of having a live astronomer in the observer's seat with the GVT is the ability to rejig and adapt your observing program as data come in. And we didn't really have that with a lot of the surveys we did because we had to asynchronously get our data products, process them into cubes, and then queue for the following night. Okay, we really need to go back and do that block. I hope that addresses your question, Jens.
And one more question before we move on to the next speaker. Do you need all of the processing hardware to be at Greenbank to be efficient?
I think so if you want synchronous processing. So if you want to be able to see things quickly, you will need, I think, substantial computing at Greenbank, or at least dedicated computing. To be fair, I wrote all of this software in Python. And I think that the big advantage of using the Argus Plus fixed instruments with a fairly well understood setups is I think we could move to a much more efficient processing framework, single mode, limited number of science cases. I think you'd be really well set up to do sort of bespoke high performance processing and really see the results coming out quickly.